Okay, so I need to give you a couple words, and I want to highlight the thing we just did a second ago. So just a minute ago, we did this thing where we integrated over a curve some vector field f, right? You guys remember what was special about that curve? Yeah, I gave it to you, and it was specifically an ellipse, right? You guys with me on that? You went around an ellipse in a vector field, right?
Okay.
So that was like, there's some little arrows going on, right? Sure, I can't draw arrows, can I? And we had an ellipse, right? And we went around that ellipse, like maybe this way, or whatever. And what did we find out?
What's law of work?
Yeah, it cost us some work to go around that ellipse, right? You see that? We had this, like, we had negative number, right? Not 0.
You had 8/16 in order to get through that entire loop.
That's really screwy, right? Because you went around a closed thing.
Well, the flow line wasn't the same.
You guys see this? It was like uphill kind of the whole way around. You guys see that?
Well, the flow line was different.
Like, that's weird.
Yeah.
So that brings up this thing called path independence.
That staircase that never stops going up or going down.
Yeah, so keep in mind, right, that apparently line integrals don't have to make sense.
Well, it kind of makes sense if you think of it as going around and you're inducing a current, like in a turbine thing.
Yeah. So there are some intuitive examples that are not what we call conservative vector fields. So here's the gist of path independence is a vector field F is called path independent if the integral over C1 of f dotted with dr is the integral over C2 of f dotted with dr for any paths C1 and C2 sharing endpoints. So the reason I bring that up in the context of this looped path, right, is that if that looped path is C1, right, and the path that just stays here is C2, you get different answers out of these, right? So that vector field F that I was dealing with before, it's not path independent. You guys see that? Because in a path independent field, if you go around a loop, you'll get 0. Because you didn't have to go around that loop to have a path with the same endpoints. You guys see that? Please note too here, when I say sharing endpoints, don't do this thing. This is a path with those two endpoints, right? Backwards does not share endpoints with this thing.
Okay.
You guys see that? So that's, they share a beginning, and they also share an end.
But one.
And the beginning of one is the beginning of the other, the end of one is the end of another. You guys see that?
Don't you mean the beginning of one is the end of the other, the end of one is the beginning of the other?
No. I mean, they have to be the same.
Oh, I was
The
saying
beginnings have to match and the ends have to match.
Okay.
Not just the endpoints as a group have to match.
Okay.
You guys see that?
Yeah.
Because otherwise, forwards and backwards should have to have the same line integral, right? And if the vector field helps me in one direction, it's going to hurt me in the other. So the only vector field that has path independence for that way and then this way, right, is probably the 0 vector field. Probably. I hesitate to say that for real, but under reasonable assumptions, it'll be the 0 vector.
Something that's perpendicular the whole time with minus that.
Yeah. Yeah, so depending on how, if you say on any path,
Oh, you're right.
forwards and backwards, then I think you get the zero vector field. But you can certainly conjure a vector field where an out and a back have zero integral by putting it all perpendicular or something. You guys all cool with that? Okay, so this is path independence. Path independence is at least a little bit related to another thing.